at sea with hundreds of fathoms of water under the keel, extremely accurate fixes are not of urgent importance. But in pilot waters where rocks and shoals abound, an exact position is of vital importance. Because of the varying depth of water and dangers to navigation, frequent changes of course and constant vigilance are required, and even a slight blunder may result in a serious disaster and loss of life. Therefore, piloting is the art of conducting a vessel in channels and harbors and along coastlines where landmarks and other aids to navigation are available for fixing positions. The first requirement of good piloting is to fix the position of the ship accurately and frequently by taking bearings of known landmarks. The navigator knows the appearance of a landmark, such as a lighthouse, because he looks it up in his light list. For example, Cape Henry Lighthouse has this description of its shape and color pattern. He can also find in this list such information about the light station as fog signals, radio beacons, distance finding stations, weather signals, or any special aid to navigation. To secure the bearings of these landmarks, a compass repeater and a bearing circle such as this may be used. The bearing circle rests on top of the compass repeater. It may be turned on the compass repeater by two posts. The bearing of an object is obtained by aligning this near vane and this far vane with the landmark, in this case a lighthouse. When the quartermaster sees all three in line, like this, he calls out mark, and the assistant navigator records the time and bearing. In modern installations, an alidade is used. An alidade is essentially a telescope mounted above the compass card so that the axis of the telescope can be rotated to point in any direction. This instrument is the self-synchronous alidade. There are crosshairs in the optical system for observing the bearing of landmarks. The bearing is read on this outside scale. To ensure accuracy in reading the bearings, the telescope is synchronized with the gyro compass repeater card so that when the alidade is set on any bearing, it will maintain that same true bearing regardless of maneuvers of the ship. Nearly all compasses have some error, however small. Any bearing observed must be corrected for this compass error before it is plotted. For the purpose of illustration, we will assume that our compass has been corrected to give true bearings. Therefore, using the bearing of the lighthouse, we can plot a line of position from the chart symbol for the lighthouse. To learn more of how bearing lines are used to establish the position of a ship, we will sail with the USS Savannah, which is en route to Norfolk, Virginia. At 0600, the navigator fixed his position here, a beam of Diamond Shoals lightship, and plotted his DR positions ahead on course 0 at 20 knots. You will remember that dead reckoning positions are determined by applying to the last well-determined position, in this case the 0600 fix, the run made since the time of that position in the direction of the true course at the speed of the ship through the water. At 0800, the Savannah is to change course to 340. And so, at 1100, the navigator expects to be in this DR position. Note that the depths of water are indicated on this chart in fathoms. Since the Savannah draws only 4 fathoms, there's plenty of water along the projected course. But the mere laying down of a course line on a chart does not ensure that the ship will follow along that line. The combined forces of wind and current and the errors of speed and course practically ensure that a ship's actual track will deviate from the projected course. To ensure that his ship is always headed into safe water, the prudent navigator frequently checks his position by whatever means are available. This book, in which all original observations are recorded, is called a bearing book. Navy regulations require the navigator to keep this record. This column is for time, while these columns are for the names of the various landmarks and their bearings. The best way for a navigator to check his position is by means of simultaneous bearings of different objects. First, he looks at his approximate DR position on the chart in order to determine what objects are available. Here is the 0630 DR position, and he sees that bearing lines of the old tower at Cape Hatteras and Diamond Shoals lightship will give a good intersection. Here is the symbol for the old tower, while this is how it appears through binoculars. And here is the symbol for the lightship, while this is how it appears. Using the Alidade, which, since there is no gyro error, gives true bearings, the quartermaster observes at 0625 the old tower bearing 277, and a few seconds later, the lightship bearing 194. From the center of the symbol, the navigator plots the bearing line in the reverse direction of the bearing, since 277 is the bearing of the tower from the ship, and he is plotting the line from the tower toward the ship. From the small dot at the bottom of the symbol for the lightship, he plots the bearing 194. The intersection of these two lines, then, is his 0625 position and is marked 0625 fix. Note that his fix does not coincide with his 0625 DR position, which is here on the course line previously laid down. This is the common way of obtaining a fix. If 3 objects are available, a careful navigator takes 3 bearings so as to give himself a better check on his position. As the Savannah steams northward, the lightship disappears from view, and the navigator now has only the old tower at Cape Hatteras available for checking his position. At 0630, the quartermaster observed the old tower abeam, bearing 270. At 0700, it bears 230. Now he knows that at 0630, he was on this line, and at 0700 on this line. In other words, this line is a locus of possible positions of the Savannah at 0630, and this line is a locus at 0700. To find the position of the ship at 0700, we must determine where on this line the ship was located. This we do by running forward this 0630 line for the course and speed of the ship from 0630 to 0700 in this manner. It is just as if the line of position were secured to the bridge at 0630. Thereafter, it travels along with the ship, and so we carry the line forward in the direction of course 0, a distance equal to 20 knots for 1/2 hour, or 10 miles, and replot it here. This, then, is a good approximation of our position at 0700. You will observe that the navigator labels this position with the abbreviation R-fix, or running fix, which means that the lines of position for the fix were not obtained simultaneously. One of the lines had to be run forward. This line is labeled 0630, 0700, as it is the 0630 line advanced to 0700. The 0630 bearing is recorded below the line. If it be run forward accurately, a perfectly accurate fix can be obtained. But the course and distance may be in error because of course and speed errors, and because of wind and current, all of which you will remember we group under the general term current. If there were a current acting in a direction 020 at 1.5 knots between bearings, the line of position would be carried forward like this, and our advanced line of position would be here at 0700, and this would be the actual position at 0700. It must be well appreciated that the accuracy of a running fix depends upon the accuracy of the run forward. For if the speed had been greater, the fix would have appeared to be here, while an error in course would have put it here. Unless this run is exactly known, too much reliance cannot be placed in a running fix. To show another graphical method of arriving at a running fix, we remove all the lines but the bearings of Cape Hatteras at 0630 and 0700. Now, abreast the run in the same latitude, the navigator measures off the run for 30 minutes, 10 miles. He sets his drafting machine to course 0, then moves the drafting machine out until the distance between the two bearing lines is 10 miles along the ruler. This, then, is the 0700 running fix. If we bring back the lines which we plotted by the other method, you can see that this position is identical with the previous 0700 running fix. Finding himself probably outside his DR plot, the navigator changes course to 356. To see that his new course will not take him into trouble, he checks ahead along the ruler. Now, erasing the old DR, he plots the new for course and speed since the running fix at 0700. And so the Savannah proceeds up the coast, with the navigator checking his position every 15 minutes when possible. Using the bearing of Bodie Island Light and of the buoy shown here, he plots a fix. He would prefer to use other landmarks, since buoys may drift out of position. But along this stretch of coast, they are the only navigational aids available other than Bodie Island Light. At 0800, he changes course to 340 as previously planned. About 0930, the lookout picked up Currituck Beach Light off the port bow. At 0938, the light was broad on the bow, bearing 295. Let us suppose that the navigator wishes to know at what distance Currituck Beach Light is past a beam. He could plot a running fix when the light is abeam, but there is also a mathematical solution called doubling the angle on the bow, based on the fact that in a triangle where this angle is twice this angle, these two sides are equal. You will remember that the light was broad on the bow, or bearing 45 degrees from the course at 0938. The navigator keeps a close check on the light and observes that it is double the first angle on the bow, or 90 degrees from the course, at 10:12. The time between bearings was 34 minutes, and the run was therefore 11 3/10 miles. Here are the two bearing lines, and here is the course line, which has been drawn so that the distance between the bearings is exactly 11 3/10 miles. This particular bearing, where we have a 45-degree right triangle, is called a bow and beam bearing.